Okay, so let's do it. So, okay, so thank you for coming along to another SNAPP seminar for this semester. This week I'm delighted to have a host, Rhonda Reiter, here. Just to explain, Rhonda Reiter is a professor and also used to be the chair of the Department of Industrial Engineering Operations Research at University of California, Berkeley. She also used to work at Santa Clara University. She received her PhD from IEOR in Berkeley as well, and applied maths in undergraduate in Carnegie Mellon. Her primary interests are in stochastic modeling optimization applied to service systems, manufacturing, telecoms, and large-scale computer systems. She's been associate editor, or she is associate editor at Queuing Systems, Probability Engineering, Information Sciences, Stochastic Models, and Informs Service Science Journal. She's also been on the editorial boards of Management Science, Operations Research Letters, Journal of Scheduling and Naval Research Logistics. And she's also the past and founding chair of the Applied Probability Society of Informs. And she currently serves on the APS Prize Committee. And I guess through the APS is where I first met Rhonda. Rhonda probably doesn't realize it, but she was actually one of the first academics I met from outside of sort of in the world. So back at the Applied Probability Society meeting in Eindhoven, where I went for dinner with a bunch of us PhD students, Rhonda and Richard Webber, and went for dinner. She probably doesn't remember, but it's one of the first things like, oh, someone from outside. It's sort of very scary, but so anyway, so
okay. Somehow I was thinking we met at Oberwolfach.
Yeah, we did. Oh, yeah. But APS was even before that, actually, I think. Yeah. So we met over Wolfpack as well. So yeah, but so anyway, Ron's been doing lots of fantastic work on matching systems. She's going to be giving a talk about service and matching systems with compatibility constraints. So.
Okay, thank you. Thanks so much to everybody for the invitation. And yeah, this is joint work with all these folks, and Christy Gardner is also on she will answer the hard questions. So here we go. So let me give the setup of the basic model. Whoops, I missed a page. So the basic model with service compatibility. So it's a queuing model, but not all servers can do all jobs. So we have Poisson arrivals of jobs or patients, and for right now it may be a little bit easier to think of, say, patients arriving, different job classes, and then we have exponential services or arrivals of, say, organs for transplant for these patients according to a Poisson process. And there's this bipartite matching structure where this class can only be served by these two types of servers, or this patient can only accept organs from these two types of donors. We have the jobs that wait in the queue. So it's a one-sided model. The servers or the organs don't wait. And so we can think of having, since it's exponential service, dummy service completions that are just lost if they're not used. An arriving organ is assigned to the first compatible patient or job, and first patient or job can be served by the first arriving compatible organ. Okay, so the three applications of this basic model. The first one is this one-sided matching, where the patients arrive and wait in the queue and the organs disappear if they're not matched. The second is a collaborative service model. And again, this is because of the exponential service. If this is a job here that's first in the queue, and we keep track of all the jobs in the system in this queue, then that first job can be served collaboratively by a server of type 1 or type 2. So they can be in service on both servers, and the service rates are added. And that's the same as cancel on complete redundancy. We could send copies of the job to both of the servers, and if it's the first in the queue in both places, then they'll both work on the job, and we'll take the minimum. And again, because it's exponential, the minimum is just as if adding the rates, and whichever one finishes first cancels the job on the other server. Now, it's also sort of the non-collaborative service model where you can't collaborate, but here it's only the jobs in the queue that are represented here. So This picture now means that these two servers are busy with other jobs, and this first job is in the queue, and it will be pulled out of the queue at the rate mu1 plus mu2 when either one of those servers become available, and then it'll just go beyond one of the servers. Okay, so we have a detailed state for our basic model where we just keep track, and we will almost for most of this talk, it'll be first come, first serve service, and we will keep track of the jobs in order of arrival. So in this picture, this is jobs 1, 2, 3, 2, 4, 1. Okay. So a roadmap for what we're doing today is I first want to talk about these product forms and a generalization called order independence, and that gives us an easy way of thinking about the product forms. And then from the detailed state, we'll think about more aggregate measures such as waiting times for a class of jobs. And then look briefly at when does collaboration help, and some extensions and conclusions. So I'm about to launch into some math here, but this is to remind me to pause, make sure we're on the same page for the basic model and how it works.
I have a quick question about the basic model. So each job only requires service from one server, or it could require service from multiple servers?
It's not so much requiring, it's that a job, if it's compatible with multiple servers, then the multiple servers are allowed to collaborate and work on that job, if it's the first in the queue. So all the compatible servers can work together for that job, and then that job is speeded up.
I see. So speed it up in the sense that it's the minimum of multiple exponential service times.
Right, and therefore it's the same as the sum of the rates. So you can just think of them as collaborating on that job with additive rates.
I see. And are you required to do that? Because it could be that I could allocate the other server to the second job in the row, or
right. We're getting there.
Okay.
So right now, this basic model is for this special case, and it applies to the queue in that other model, because while you're in the queue, if either of your compatible servers completes, you get to go and be on that server.
Okay.
So it's just the queue part. We haven't gotten to the other part yet, but just the queue part. And then, yeah, we'll come back to the non-collaborative case, the case where they can't work together.
Thank you.
Okay, thanks for the question. So now that we're on the same page for this basic model, I'm going to generalize back up and look at a more general framework, which is back from the 90s. Krasinski and his co-authors. So this is order independent queues. So now we have classes of jobs. It's a multi-class service system. And we keep track of our classes of jobs. And then we just have a generalized service process that's just a function of the classes of jobs in order. So right now it's just some general function to define its properties. Let's also define these first differences. So the delta sub I Cn represents the service rate allocated to the ith job. So this, say the second job here in the system. And so the total service rate is you add up the amount allocated to each one. So just remind us, and now what are the properties? So the first property is that for this marginal service rate that you give to the ith customer in the queue depends only on that jobs class and all the jobs ahead of it, but does not depend on the ones behind it. So we're assuming first come, first serve, so that's going to give us pretty much right away that how much service this job gets doesn't depend on the jobs behind it. And then the second property is that the total service rate doesn't depend on the order. And the first two tell us that the total service rate up to any I doesn't depend on the order. So we can rearrange to get that first service rate for the first 4 jobs is the same regardless of what order they're in. And then as a technical condition, we need that it's non-idling. So again, our basic model is order independent. It satisfies these properties. So we have that the service rate, say, to the second job here is mu3, and it doesn't depend on what's behind him, behind that job, and that the service rate is the same for all permutations up, and the total service rate up to any I. So these first 2 jobs will get served totally at rate mu1 plus mu2 plus mu3. It does matter which one gets the service, but the total service rate applied to the first 2 jobs is just the total service rate of all the compatible servers to those two jobs. And then with just those properties, you get this product form result. So to get the probability of being in this state with this set of job classes in order, you just multiply and you have 1 term for each of the job classes. And I'll give you an example in just a minute. But because our basic model is a special case, we get this kind of product form for, in the collaborative case, this was shown earlier, and in the matching case earlier, but sort of re-derived in a more complicated way. Okay, so here's the example. We can get the overall probability of being in this example state is our normalizing constant. And by the way, I'm not getting into questions about when is it stable or not. In this particular, in our matching model, the conditions are kind of obvious conditions, but these results hold when those stability conditions hold. And then we have, so we can get this normalizing constant, which is the probability that you have 0 in the system. And then the first term is the arrival rate of the class that's first, divided by the total service rate applied to the first job. The second term is the arrival rate of the second job, divided by the total service rate for the first 2 jobs, and then the third, and the total service rate of the first 3 jobs, etc. Once we get up to this job of class 4, it can be served by all the servers. And so now the denominator is the total service rate for it and everything in front of it. And after that, we're just going to have this mu total service rate in the denominator. Okay, so, and what can we do with this? Well, so this is both, it applies to extensions as well as the proof. So let me remind you, quasi-reversibility, that means that the state is independent of the arrivals after time t and the departures before time t. What matters for us for the proof is that you can use partial balance to prove your steady state distribution. And for us, what does partial balance mean? It means the rate out of state I due to a departure balances the rate in due to an arrival. The rate out due to a class C arrival balances the rate in due to a class C departure. And then we get Burke's theorem that the departure process is a Poisson process, and we can glue stuff together and get a product of product forms for networks of these queues. So let me just, the proof, once you look at it through this order independence view, is immediate. So I'm going to kind of give you the idea. So we want to show that this product form satisfies global balance, and partial balance implies global balance, because if we have the rate out due to departures, balance, rate in due to arrivals, etc., we add up all these rates out and in, we get the total rate out is equal to the total rate in. So we just need to show partial balance for this equation. And we're going to use start off using this recursive form. So I can write the probability of being in state N as the probability of being in the state with of length n-1, the first n-1 jobs, with this extra arrival rate of the nth job divided by the total service rate. And that's basically going to get my first balance equation. The rate out due to a departure is the probability I'm in the state times the rate out of that state, and that's just this times this, equals the rate in due to an arrival. And the only way in with an arrival is if I get that class CN job coming to the end of the queue. So that's, kind of what tells us to expect this kind of product form. To go the other way is just a few lines that I'm going to spare you, but it's, it's basically 3 lines that follows from property 1, property 2, and then some algebra. Okay, so once we have that product form, now we can extend to networks, as I said, because it's quasi-reversible. We can have abandonment because that still satisfies this order independence. The job that's ith in position, its rate now of overall leaving the system through either being served or abandoning only depends on its own class and the classes of the jobs in front of it, and not on anything behind it. They abandon or whatever, it's not going to make any difference. And the total rate at which jobs leave the system, either through service or abandonment, doesn't depend on the order. And then we can have finite buffers. That's no problem either. So we just say, not all jobs get to come in based on who's already there. We just need a couple of properties for that. And the first one is basically order independence, that if you decide you're going to reject an incoming job, then it's based on the classes of jobs that are there, but not in their order. And then the second one's kind of a monotonicity thing, that if you have more jobs, you add a new job of a given class to a set, you're going to be even more likely to reject than you were when you had a subset of the jobs. And so this kind of rejection region includes just having a single shared buffer of a finite size, or having class-dependent buffer limits, so queues on the job size, or server-dependent buffer limits, queues on the server side. All of those satisfy these 2 simple properties. We can have speed scaling, so you can, depending on the total number in the system, you can speed up or slow down with this gamma of n factor. And you can do scaling of the arrival rates, and you still get a product form. Okay, and before I move on to the 2-sided version, maybe I should pause here just to see if we're on the same page. Those product
I have a question again, to just a clarification. So you mentioned this property about so basically there's certain property about what happens doesn't depend on what is behind me. I assume, I guess in addition to the policy you gave an example, there are many other rules that would satisfy that condition, or does that uniquely define what policy?
Oh, no. So that's a good question. So Krasinski and his co-authors were looking at cases where you could only have at most a certain number of a certain class in process at the same time. So if you already had 2 of the same class being served somewhere, and they didn't have this collaborative service, they had separate service. If it's in service somewhere, then you can't have another one of a particular class. I believe that's how it was. But anyway, yeah, they had a completely different application that they were looking at, and nobody realized that it applied to this one.
I see. Thank you.
Can I ask a point of clarification,
Yes.
Rhonda? So going back to the original question that Jean asked, you have to just have a convention a priori on this collaborative service, how you're going to do it, whether you're just going to give, right? You can't have some mix and match strategy because the way you do it has to just depend on the future queue.
That's right. It's essential that it's first come, first serve. So
Yeah.
whatever job is first gets all its collaborative servers working on it. And then the job that's second, if it's of the same class, it's going to get nothing at all. But if it's a different class where, you know, maybe some of the servers are being used by the first one, but it gets to use a different one next, then you can. So that's the protocol.
Okay. Yeah, thanks.
And Varun, did you have your hand up?
Yeah, so I mean, since the proof looks a lot like the PSQ, I was thinking whether like if you could sort of aggregate service where like you just care about the number of jobs of each type and then you split capacity equally over them.
Because then the jobs behind you are going to matter. Because there's more people behind, I'm going to get less service.
Right. So is there a different state space where instead of like the ordering mattering, if I just look at the number of jobs of each type, would I get product from in that state space if I have to?
That's a good question, which I don't think I can. I have to sit down and think about that. But I don't know. I mean, I guess you know, processor sharing is something people have thought about. So if, you know, I don't know that there's anything new here that's going to help with that question, because this really does, for the order independence condition, really does depend on first come, first serve. And our model also definitely does. And it's, you know, that balance, partial balance, it's because you're adding a job at the back of the queue. And okay. All right, so now let's think about a double-sided queue. So now if we think in terms of the patients and the organs, some of those organs can stay around for a little while. So why not keep them around or keep around the unmatched servers? So now we need a buffer for extra servers. And we have our buffer for jobs. And now the unmatched servers also wait for a match in first come, first match order. So that's going to again be essential, is that now we have, you know, multiple servers or organs of type 4, and they will wait in order here and get matched. The first one that arrived or became idle will get matched to the first of the jobs. And here, even with those other stability conditions, that basically that for any subset of job types, job classes, there's enough service capacity to serve them across all subsets. Now, in addition, with this two-sided bipartite matching, we need extra conditions for stability. So abandonment or finite buffers on at least one side. And the applications are organ matching when they last, organs last a while, or ride hailing, or it could be now more of a manufacturing thing where before it was all make to order, the customer had to be in the queue before you would bother to make the product for them. But, you know, maybe you could make some hamburgers or whatever ahead of time, ahead of orders, so you don't have those kind of dummy service completions. They actually, you know, produce something and stick it on the shelf. So now we need to keep track of the servers in order, or the organs in order of their arrival. And so we have this service vector 4.4, and now we have what rate are servers served. Well, servers leave when compatible jobs arrive. And so the service rate here is the total arrival rate of jobs that are compatible with 4. So in this example, that would be lambda 4. We're waiting for the job, and that would pull a server out of the server queue. So now, and we can define this delta, the amount of marginal service from the server queue, the rate at which the ith server can leave the server queue as this, marginal amount. And these, it really is completely symmetric. These satisfy the same order independence properties. And so now, you have to have appropriate admissible states, because you can't have jobs and servers both in the two queues that are compatible with each other. They would have left. But as long as you're in the appropriate admissible region, you get the same product form. Now we have terms just like we had before for the jobs, and then terms for the servers, where mu is the arrival rate of that server class. Now we have classes or types of servers, the arrival rate of that server class, and then the lambda here of compatible jobs for those first I servers is the departure rate for the ith server in the queue. So here's an example where we have the first terms look like what we had before, and then we have these extra server terms that can, with total rate at which they leave is lambda 4, regardless of where they are. And again, we can have abandonments on either side. You can have the speed scaling and the more general rejection regions, et cetera, all of that. It's all really is completely symmetric. Okay, so now let's get to this non-collaborative, this cancel on start type protocol if you're doing redundancy, where you can only have one job in service at a time, not other jobs. So these C's will represent the jobs in the queue. So I'm going to block them out if they're already being served. And the S will represent the idle servers in order. So this is known as the Alice property, assign longest idle server. And again, the classes of jobs that are not in service, that are in service, are not in the queue state. So they're on busy servers, and we don't really care about their classes anymore, because all the service times, and it is a critical assumption here, the service times, the rates depend only on the server or server type, not the job class. So again, I mean, really, it is just a two-sided matching queue, where now our rejection region for this idle server queue is that you can have at most one of each type of server. So all those dummy services, when the server is busy, are thrown away. And so you get this kind of same, it really is exactly the same thing. And this can be, so Adan and Weiss looked at this non-collaborative model with an aggregate state where you keep track of the, you have a sort of a geometric number of each type behind the first one that's being served. You don't really need to keep track of different classes as long as they're blocked. And so with this kind of aggregated state, then proving the product form with that aggregated state is quite complicated. But you could go from this to the aggregation fairly easily. So again, here's another example where we have server 4 and 1 are idle, and we can only have one of each in this queue, and then the jobs that are in the job queue have to be incompatible with the idle servers. And we have the same types of terms for the job queue. And then for the idle servers, it's again the same story. Rate at which the first one arrives divided by the total rate at which it can leave. The rate at which the second one arrives divided by the total rate at which the second one could leave, which is the second one is type 1. So it could leave if either a 1 or a 4 arrive.
And maybe I had a quick question about that picture just before. So I was trying to understand how kind of FIFO it is with respect to the servers. So does
Yeah.
that mean if something, you can't get server 1 working until server 4 started? Or is it just the case that if something works, both of them could serve that job, 4's got to do it?
That's right. That's right.
Yeah.
So it's the same as on the other side, where a job later behind, if it's compatible with something that's not compatible with the jobs ahead of it, it can get served.
Yeah.
And the same thing now on the server side, if it could be later in the queue, but if it has a class, as in this case, this server could serve type 1, the class 1 jobs. And so if one of those show up, it'll leave, it'll become busy.
Go out. Yeah. Okay. And it's just if there's like something that both of them could do, then the 4's going to go, and then it's the 1 essentially.
That's right.
Yeah.
That's
yeah.
right.
Okay. Yeah.
So first come, first match on both sides.
Okay. Yeah.
Okay, so now I just want to mention this quickly is actually Don and Weiss and their co-authors started off thinking about, rather than first come, first serve, or Alice on the server side, what if you have a random activation rate? So now you have idle servers here, and you need to be careful to get a product form. You can't just, randomly pick an idle server to assign it. It won't work. You have to pick it in just the right way. And so they have this activation rate that now is a function of the queue of busy servers. And obviously, if you know who's busy, you know who's idle, and vice versa. And here they're not keeping track of the order of the idle servers. So you keep track of the busy server, and then you need to have just the right arrival rate to your busy server queue that's going to depend on who's busy now. And there's a complicated assignment condition that kind of boils down to an order independence type of thing. You need this product to be the same regardless of how you permute the busy servers. So if you have all that condition, then again, looking at it from this view of these detailed states, it's easy to show you get the same type of product form, where now the second part of the other part of the vector here is the busy servers. And so yeah, same terms for the waiting jobs. And then this is lambda is the activation rate, the rate at which a class B sub I server becomes busy, and then divided by mu of B represents the overall rate at which any of the busy servers become idle. So it's just the sum of the service rates. Okay, and then other models that folks have proposed are can also be seen through this view. So this token model, I'm not going to spend a lot of time, but it's sort of a 2-level version where you sort of have 2 order independent queues. So jobs arrive, they need a token before they can even join the service queue, and the tokens maybe have compatibilities. And so you worry about, so you wait in line for a token, and then you move over to another order independent service queue. And this it generalizes both the non-collaborative and the collaborative models. It kind of depends on where the matching occurs before or after you get a token. And then again, it's kind of a sequence of queues, and you get product forms for each of the sequence. And they took the view for the part that was non-collaborative of doing this, of having the right activation rates to get the product form, rather than assign the longest idle token. And then the general non-bipartite matching model. So now, in a way, why do we need the bipartite in jobs and classes? So here we have just agents, and agents arrive according to a Poisson process, and they have compatibilities. An agent will depart upon arrival if there's a compatible agent. So if a yellow one arrives and there's a blue one there, then the pair will immediately depart. Otherwise, we keep them in a first come, first match queue. And so if they if a blue one, given this queue, if a blue one arrives, it would take out the first green one out of the queue. And now you need, you have to be careful with stability, but we will, given the appropriate conditions for stability, and then given now we just have the classes of agents in order. And how are agents served? Well, they're served by arrivals of compatible classes. And so it's just here we've got these jobs, and they will be served by any compatible, which is at this point any of the other classes of jobs, and that'll be the total rate out. That again will satisfy the order independent conditions, where I don't care about the agents behind me in terms of whether I'm going to get matched, and the total matching rate is just the total rate at which compatible agents show up. And so you get now a product form for this for the admissible states, where again you can't have matches in the queue. Okay, so we're kind of done with the product form and ready to move from detailed to aggregate, but let me just pause here again. I do appreciate questions as we go along, but in case anybody's saving up.
Maybe a quick question, just that last theorem, is that a direct consequence of the Brzezinski order independent work? Or is it that you
Well,
need new
it does
machinery?
take a little more work, and
I mean, I'm not saying it's easy. I'm sure it's not easy. But
yeah,
getting the
well,
model
I'd
to fit.
refer you to Celine's
yeah.
paper, so she goes through all the details. And
Yeah. I mean, I'm sure it's
yeah,
difficult
you
to
have
get the
to be
right
careful.
model and make sure it fits with the theory and all the rest of it.
Exactly.
Yeah.
And so we have the order independence. You also have to kind of be worried about the rejection region, because we kind of have both at the same time,
Yeah.
right? So a compatible agent with one of the ones that's there is rejected as an arrival. At the same time, it's providing a service for the agents that are already there. So you kind of have to check on both sides, but
Yeah.
it's okay.
Okay.
Okay, any other questions? I don't know. But, oh, sorry, it's even on my side, I'm getting this delay. All right, so I am moving into the aggregate model. So another queuing 101. I was asked to worry about the PhD students in the audience. And so this first part, we all know about MM1 queues, right? Arrival rate lambda, service rate mu, number in system is shifted geometric, the number of failures before the first success. And we all know the response time is then exponential for an MM1 queue. So that we know. Now, what some of us might not remember is for a multi-class queue, where we have arrival rates of different classes, but still a single server at rate mu, then of course, and it's first come, first serve, regardless of the classes, then of course the total number is going to be the exact same geometric distribution. The number of each type of class, if we just look at them, it's pretty easy to see that's geometric also. It's kind of a splitting property of your initial geometric, that you end up with a geometric of the different classes. And then if the number is geometric in your system, by Little's law, you get the distributional Little's law, because it's first come, first serve. You get that for the class I jobs, their response times are again exponential. They're the same response time as in a plain old MM1, but here's their geometric number. So here's their arrival rate, and here is their effective service rate. So it's as if they were in an MM1 queue all by themselves with their own arrival rate, and then the service rate is cut by the arrival rates of all the other jobs that they're taking, and they just get the leftover service rate. So now we go back to our compatible OI queues or matching model. And suppose, and this is the basic matching model, so it's just worrying about one side. And suppose we have some class that is fully flexible, or even in the OI queue, you can do this analysis where there's just some class that when it's there, all the capacity is being used, not necessarily by that job, but by somebody. So if you have a job that matches all the servers, you know all the servers are busy in this collaborative model. You know if you have an organ recipient who matches all the possible donors, you know that if any donor organ arrives, it'll get matched to somebody. Okay, so this first flexible one, the jobs behind it get no service. So it's as if they are in an MM1 queue altogether, and they're following this kind of combined Markov chain at total rate lambda, total service rate mu. The jobs before, because of our product form, you know, we just have this product of stuff, and then there's this class J and more product. It's as if they weren't there, you'd have the same product form. So it's pretty easy to see that ahead of that job, it's as if you have a system with no J jobs and the exact same math. And so therefore, up back of the queue, you have the total jobs here is going to be this geometric number. It's just this number in an MM1 queue, and the number of class J jobs, when there's J jobs there, or not when there are, but the number of class J jobs will be this shifted geometric. There's a certain chance you'd have none and one, etc. And with, look at that, with this same lambda J over mu minus the sum of the other rates, which I realize now I wrote that wrong down there. It should be, say, little j not equal to capital J, but all the other jobs. So the number in the queue is the same as in the standard multi-class MM1 with first come, first serve queue. And therefore, again, arguing from distributional Little's law, if you've got geometric number in the queue and it's first come, first serve, the service distribution has to be this exponential, and so it's the same as in any MM1 queue with arrival rate lambda J. And again, that's a, oh, this time it's not a typo, with service rate mu minus the arrival rates of all the other classes. Okay, so we know in these order independent queues, if you have a customer that can get, you know, if there's nobody in front of it or whatever, get served by the whole capacity, then you get this MM1 response time. You can break it into pieces, which will be useful when we think about the other jobs, where there's the queuing time for this most flexible job, and then there's the service time for the most flexible job. And if you sit down and think about the analysis from the miracles of the exponential distribution, if you define the service time as the time at which that most flexible class job starts service anywhere, it might not start service at all the servers at the same time because they could be busy with earlier customers, but whenever it starts anywhere, then the whole distribution until it leaves is kind of this mixture of sums of exponentials, and it's still exponential. So indeed, its experience of the service time is the as if it has exponential service at rate mu minus the rates of the other jobs. Okay, so we have the queuing time and the service time, and now all the other classes of jobs have to wait for basically a queuing time of the class J customers. If nobody's there, if there's no class J customers, it's as if it's not there and you're done. If you do have class J customers, then you have to wait for their response time. And so it's essentially a queuing time for them. And then it's this other class, whatever class it is, I, response time given, because it drops into this piece, no class J jobs. So that we can now kind of bootstrap this to get sort of a series of queues when we have this nested structure. So a nested collaborative structure means that for any job class, the servers that are compatible with that class, compare it with some other class, either one is a subset of the other or they're completely disjoint. And we have that here. And a property of that is that you get this recursive structure. If you take, you'll end up either it'll be disjoint or you will have a fully flexible class. And then when you take it out, you'll get a new substructure that has a fully flexible class. And we can keep going down. So we can sort of bootstrap, this is a lot of notation here, but bootstrap our intuition about this fully flexible class to get a series of queues. So for any class I, we've got these queuing times for all the classes that are more flexible than class I. And for each one of them, we just kind of worry about these subsystems. So it's the, mu for that most flexible class in that subsystem, and then subtract out, all the others besides that most flexible one. So their queuing time, and then the response time when you finally get down to the class where you are the most flexible. So here, let me show with an example, it'll be a little easier. For class 1, it has a queuing time for class 6 jobs. So it has to wait for all the class 6 jobs to get out of the way, if there are any. And then it drops down to here, and it's just class 1 and class 2 here, but class 2 is more flexible. So it has a queuing time for the class 2 jobs for this subsystem where there's only these jobs. And so queuing time for class 2 is lambda 2, and then this is the service rate that class 2 sees, the total service rate minus the arrival rate of class 1 jobs. There may be a typo there too. And then finally, the response time, now you're down to the point where it's just class 1, it has its own private MM1 queue, and so it has its response time. Okay, so that's all really nice and elegant. Now, what about the non-collaborative? Non-collaborative really is a lot harder. You can bootstrap this because the non-collaborative queue, stuff that's happening in the queue, when servers are busy, is acting, on sample path basis, completely equivalent Markov chain dynamics as the collaborative queue while they're busy. So you can get the same, sequence of sort of response times while you're queuing, but maybe you don't need to queue, so you have to worry about that. And then once you're done queuing, the service time, once you fall out, depends on which server you get, because the news are different for different servers. And, so extra math to kind of figure out whether you have to wait at all, and then if you do, which one you're going to end up on, because, the servers are doing longest idle order, whatever. So it's, even though it's nice and beautiful for the collaborative case, and you can apply it for the queuing time conditioned on the servers being busy, it's still hard to get a whole nice picture for the non-collaborative case. Okay, so let me just summarize what we have. So this order independence detailed states gives us common framework and way to think about all these things, and really very easy proofs for a lot of models that have been there and are coming out now. Those original proofs were often much more aggregated, aggregated and complicated. Complicated partly because of thinking in an aggregated state framework. But then, if you want to get class-based things, you kind of have to aggregate across classes. And so that's what we just did for these nested situations, then you can get nice, clean results. And so now I'm going to move to comparison of the collaborative and non-collaborative, but let me.
It's not.
Okay, any questions on waiting times? Arun?
So this is maybe more on maybe both proof and the abandonment model. So is the proof for the result that you showed, is it like a coupling argument, or is it sort of you look at the detailed state space and then from that you sort of figure out what the waiting times are and then say, oh, it looks like the distribution that you have written? Because I'm just wondering in terms like for the abandonment case, suppose I have abandonment, can I still write this stochastic equivalence even though I can't figure out maybe the terms on the right hand side either?
Yeah, so the abandonment, that's a good question. So that the analysis I did kind of went back to the first basic model without abandonment. And I think, I don't know, I'm not sure about the abandonment. I don't know, Christy, do you have thoughts?
Well, I think that you could still draw the same relationship between the queue in the non-collaborative model with the system in the collaborative model. But I know with abandonment, there's just, it's really difficult to do any of this aggregation to get any sort of system metrics, just because the denominators in the product forms become so complicated because there's a different term, a different additive term for every job. So I don't think we can do very much in the case of abandonments.
Yeah, so I guess, you know, the basic idea would still hold for, say, the most flexible job would probably experience, I mean, I guess that would still be the same as a plain vanilla MM1 plus M abandonment queue, which is already kind of messy, but that, I think that experience of that job, but it's just, you know, that's messier anyway. Okay. So this last part is quite quick and I'm running out of time, so I'll make it even quicker. I just wanted to kind of an overview on, now let's compare what's going on. So when is collaboration better? So if you have just a plain vanilla MMK system, or you can even have heterogeneous servers, the Muse don't all have to be the same, then we kind of all know that you glom all the servers together in terms of at least response times. You'd like to have a single fast server. So that's good. And that argument can kind of be extended if you have different servers, but with the same compatibilities. So they're kind of indistinguishable. It would be better to glom them together with each other and have a fast server. So, and that's what collaboration does, is make it a fast server. When things are fully symmetric, and a fully symmetric system means you can interchange all servers and jobs. So that means all the lambdas are the same, all the Muse are the same. And essentially the matching graph has to look the same everywhere. So that's one of these power of D type situations. And then you can do variants of a symmetric W model. So like a nearest neighbor model, like some of these bike return models. The M model, as long as it's symmetric, we get collaboration is better for all of these things. And the intuition is that collaboration reduces idling. If you have just one job in the system and multiple servers that can work on that job, then in the collaborative case, they can all be working. Otherwise, some of them may mix it up. Is it always better? And well, I guess, you know, me coming from Berkeley, the left coast, it's like my first reaction thinking about this is, yeah, collaboration should always help, but no, it does not. And it's really when things are asymmetric that stuff goes wrong, and it can go very badly wrong. So here's a really skewed asymmetric end model and a trajectory where the difference between what you would have, and this is now driven by the same arrival processes and service processes, can get arbitrarily large. And there's a sample path proof that if you do drive them, then there's just no upper bound on the difference, which will be in contrast to the other way. So how about the benefit of collaboration? So the cost could be unbounded, the mean cost could be unbounded depending on the parameters. You can cook up parameters that can make it arbitrarily bad. But the benefit is always bounded. So that's a little sad. You can get some benefit from collaboration, but generally not all that much. And a loose bound that you can get just from this idea of so now the superscript means non-collaborative. The non-collaborative number in the system is the number in the queue plus the number in the server. And by arguing with this analogy that what's in the queue is kind of the same as what's going on in a collaborative system, you can argue, okay, well, you got the ones in the queue and then you got the ones in the server. And it's basically the difference between the two is bounded by the number of servers. And you can extend that argument to each individual server class with counting the number of servers they could be on. So they're either in the queue or on those servers. So that's unfortunate, but. And then quick extensions, what if we schedule, and how about the impact of flexibility? So can we do better than first come, first serve? It turns out least flexible first, when it's nested, is the optimal thing to do. And then if you do things optimally, collaboration is always beneficial. So if you're doing optimal scheduling, then collaboration can always help you. For nested systems under the optimal least flexible first, then more flexibility is always better. I'm going to skip this. We have a way of adding flexibility in combination with scheduling to make everybody better off, each class-wise better off. I'll skip that. And then the impact of flexibility, again, more flexibility helps when it's metric, but if it's asymmetric, it can hurt. So here we're adding flexibility by shifting jobs from one of the two dedicated classes to collaborative flexible class. And as you do that, the mean response time, initially it goes down a little bit, but then it goes up. On the other hand, under this least flexible first and other policy, more flexibility always helps. And we have some results on kind of convexity. Okay, so flexibility always helps, but how much, and kind of a second order effect is you do get symmetric, it's a little, less sharp, but here in the asymmetric case, just a little bit can make a huge difference. So order independence gives us this nice detailed state. Nested systems, we can aggregate and look at get some nice results for response times. For first come, first serve and asymmetric systems, collaboration and flexibility can be arbitrarily harmful and the benefits bounded. And then if you schedule optimally, then collaboration and flexibility helps, but there's diminishing marginal returns. So those are the takeaways. And if you're interested in the particular papers, and we have this kind of more survey paper, this overview paper that has most of what's in here. So time for a quick question. I'm sorry about.
Okay, well, okay, thank you very much, first of all. Perfectly on time there.
Well, we are minus time for more questions. But.
That's fine. So yeah, are there any questions? I had maybe some thoughts / questions, but we had quite a few whilst we're going along. So you sort of listed my favorite properties of like quasi-reversible systems, like being, got to route things between queues and truncation and things like that. The one you didn't mention, which I sort of know why, is because it is insensitivity, and I think Varun sort of alluded to that as well a little bit. So I mean, and then I was thinking like, well, obviously it's a FIFO thing, And so, and insensitivity to kind of processor sharing and things like that. And so maybe that's why. But then you have things like last come first served is insensitive. And you can kind of imagine there might be something like an order independent version of last come first served. And then, it's wondering if there's any hope of getting something like that at all.
Well, it would require a shift in the framework, because this really, this is like these different classes, and the order matters, and so and it does depend very much on the.
You go in the refrigerator, put the garlic away.
Sorry.
Don't worry.
Okay. Yeah. So maybe, but it's and maybe somehow for special cases, something, some nested something, maybe.
Because you have to define the muse also in the opposite way, right? So the people behind you matter and not the people in front of you. And then maybe if you sort of combine the ordering with like how the muse are defined, it could still work out.
Yeah, maybe. But it's a good thing to think about.
Because it just I mean, like I read the Krasinski paper after having seen a bit of you guys work on it. So it seems like it's just the perfect set of conditions for that FIFO system, and it's sort of, you know what I mean? It's sort of it's sort of like the definition comes from the property of reversibility sort of for FIFO, and you sort of wonder if there's. I mean, I haven't really tried to think about it in any serious way, but.
Well, there are Compton and Dorsman have this pass and swap thing where it's kind of somehow taking into account what's going on behind, but where the first service comes and kind of offers it, maybe not explaining it all that well, but offers to the first one in the queue and sort of makes it, instead of disappearing, it goes back and finds a later compatible job and replaces it. And that one could leave unless there's another one that's compatible behind. And so it's a way of kind of propagating the order backwards.
So it's like as soon as something new comes in, you got to stop what you're doing and everyone kind of moves there, that kind of thing.
Yeah. So, this particular lambda over mu thing at the individual level just kind of gets messed up when you do that.
Okay, great, thanks. Any further questions? Like I said, there are quite a few during the thing. I'll give one last round of applause, and if people want to hang out, then.
Thanks. Stop sharing. Oh.
Thank you, Rhonda. It was really nice
Private
seeing
message
you.
there.
Okay.
Yeah, so thank you very much.
Bye-bye.
Okay. Hi, Mark. Oh, bye. Mark was just messaging. I think might be having a few busy people, so yeah. Well,
yes, I think so.
Yeah,
okay.
Good to see you.
Good to see
thanks
you. Thank
for
you so
the
much.
talk, and it's a shame Siva couldn't make it, obviously, but I'm sure I'll be catching it up online. I was quite glad to catch it because I mean, I think it's fascinating. I think it's really great. Obviously I spent a lot of my PhD looking at reversible systems and things like this.
And we thought we'd seen them all, and
yeah, exactly. And there's this whole
this application is tailor-made. But
yeah, and I didn't probably say it clearly enough earlier, but I think it's fantastic because even if there is this early Krasinski paper, they weren't thinking about it, I don't think, in terms of compatibility and these kind of matching problems and things like this. And so the fascinating thing is there is this connection there. It's not like everything's a consequence because they did it all before. It's like really there's all these things that fit nicely into that framework, if you see what I mean. So I think that's really interesting.
Well, it's one of these cases where they invented the technology and then it took a while to come along with the killer app. So this is the killer app.
Yeah, exactly. I think that's right. So no, great. Well, good. Well, I hope we get to see each other maybe in person at some point.
I hope so.
Yeah. It's the world's everywhere's further apart nowadays, but
yeah. I'm toying with the idea of cores. Are you thinking about going there? The Canadian operations research?
Not necessarily. I might be over for stochastic networks in the summer if that goes ahead. It's been cancelled twice, so who knows?
Yeah,
that'll be my next chance. My wife has a conference in the States at the same time, so we might be able to, actually kind of have something vaguely resembling a holiday.
Yeah, that sounds nice.
So we'll see. Yeah, good. Well, anyway, thanks again. I'll let you get your second coffee of the day.